This video is going to cover how we measure the size of earthquakes. I have a photo here from an earthquake in 1989, magnitude 6.9 earthquake in Loma Prieta, California. And as described in the caption here, the wall support was inadequate to handle the shaking that occurred, and this building failed pretty dramatically. This earthquake also collapsed part of a freeway. This is in the San Francisco area. And it also stopped the World Series. So there's actually some real film footage of the World Series going on and the reaction by all the people. And of course, then the series was canceled for the day. This was a pretty big earthquake. Here are the learning outcomes for Unit 10B, and this particular video covers number 11. So pause and write that in your notes. So here's our outline. This is going to be a pretty short video, although I always tend to think that, and then look what happens. But we're going to just talk about two things: the modified Mercalli intensity scale and the moment magnitude scale. And these drums that are showing the squiggles that you might think of as the typical instrument reading of an earthquake, these are related to the magnitude scale. But we're going to start with the first one here. The intensity of an earthquake is the amount of actual shaking felt, and it varies by location. The scale we use is from Roman numeral 1 to 10, with a 1 being an area where there was essentially no shaking felt, and a 10 being the other end of the scale where there was catastrophic shaking. This depends on a number of factors. First of all, your distance to the actual epicenter. So here's a map showing intensity values 1 through 10 down here, and they're colored, of the 1994 Northridge earthquake that was a magnitude 6.7. The reds and oranges are these highest values of shaking on the intensity scale. And Northridge is right here. That's pretty much where the epicenter was. And so you can see there's a large area that experienced the greatest amount of shaking. As you move outwards, you tend to go to these lower amounts of shaking, and there's some white areas here where there was essentially none. Now, it's not a perfect bullseye because there's other factors besides the distance. The depth of the earthquake is also going to make a difference. The directivity, so when the faults move, remember earthquakes are from movement on a fault, there's going to be some directivity, some directions that the rocks are going to move, and that's going to affect areas around it. And then also the local geology is actually going to affect the amount of shaking as well. So this is a qualitative way of measuring an earthquake. This is how much shaking did you notice where you were, what happened exactly. Here's the scale, and it is, as you can see, just qualitative. So a 2 might be a weak intensity, felt only by a few people at rest, especially on the upper floors of buildings. Whereas if we get to a 7, this is damage negligible in buildings of good design, slight to modern damage in well-built ordinary structures, considerable damage in poorly built or badly designed structures, some chimneys broken, etc. So that's the scale. Now, just to go back to that idea of the bedrock or the local geology, when the earthquake waves pass through rocks, they go at different speeds depending on how densely packed that rock is. They go faster when it's more dense, and they go slower when it's less dense. And so what we're seeing here are 4 different kinds of rock units, or some of these are actually sediment. They're not even solid rock. And then the way the earthquake waves would squiggle as they go through them. And this height above what would be maybe like the 0 line is called the amplitude. How much does that needle deviate from where the 0 line would be? So the hard igneous rock is the most dense of the group here, and so the shaking would be there, but it might be pretty minor compared to once it enters some sedimentary rock, which is less dense. And now we have larger amplitude shaking. Alluvium can be somewhat solid, but it could be loose gravel surrounded by sand and silt and clay. And that's even less dense, so we have more shaking. And then finally, silt or just mud would create a large amount of shaking. And in fact, the bridge collapse that I showed you in the Loma Prieta earthquake was built in one section on silty material, and that is the part that failed. This is from the United States Geologic Survey. It's kind of a poster advertising the earthquakes and the what you feel when you feel that shaking. And it talks about the different things that control that shaking. And I've just put this sentence down here to remind you, this is a qualitative statement based on observations. So they have a map here showing an earthquake. The epicenter is here, and they have the magnitude listed as 6.4, and we'll talk about that magnitude next. But then they are also showing the intensity. So these colored lines are showing zones of different values of intensity. If you happen to be here when that earthquake occurred, you felt level 8 intensity. If you were a little farther over here, you felt level 5. Out here, you felt level 3. So that's generally the idea. Here are two more maps showing the shaking intensity of two earthquakes in California. On the left, we have the Sylmar 1971 earthquake, was a magnitude 6.7. And what you can see is a pretty good bullseye of shaking, which is greatest at the center where the epicenter was, and diminishing outwards. This one on the right is a little more modern. We call these shake maps because we have modern computers. These are actually put together pretty quickly when an earthquake occurs. And remember, this is a qualitative statement. So how do they get this information? Well, people voluntarily report what kind of things happened if they felt the earthquake. So here we have the highest levels are in red, and the star is indicating the epicenter. This was an earthquake in 1984. And then you can see all around it how the shaking was reported. So you too can report an earthquake. All you have to do when you feel an earthquake after you're safe and it's stopped is you can go to your computer and you can Google, "Did you feel it? Earthquake?" And it will bring you directly to the site that you need to go to. And so I've shown you here how that's the first thing that pops up. And when you go to it, you get to the USGS page. Did you feel it? Now on the right-hand side, there's a list, and I've only shown a little bit of it, but there's a list of earthquakes in the past 24 hours, and maybe you felt one of them and you would click on it. So for example, if you were in Stanton, Texas, and you felt this one, you would click on it, and then you would answer a series of questions such as, were you inside? Were you outside? Were you on the ground floor? Did things rattle? Did things fall off the shelf? So they'll just ask you all of these descriptive questions, and you just say yes, no, and things like that. You don't have to give your name, you don't have to give your address, although I do think they encourage you to give your zip code, so at least they know where to put this information on their maps. If you happen to feel something that's not in this list, then you could report an unknown event, and it'll be the same series of questions. So there you go, you can contribute to earthquake science. Okay, now we're going to move on to moment magnitude scale. And you might think of this as what we call the Richter scale. And the Richter scale is very similar, but the moment magnitude scale is a little bit more modern. And it's basically, you can think of it as an updated Richter scale, but they're both based on measurements made with instruments. So magnitude is a measure of the energy released during an earthquake. This is determined by looking at the seismograms. So this reading here of the squiggles is a seismogram, and looking at the amplitude of the largest waves. And we're not going to talk about these different waves in this class, but here you can see the amplitude seems to be largest over here with something called a surface wave. And so they would measure that, and that would tell them about the energy released. So here's a table showing earthquakes from 2 to 8. We do have earthquakes that are smaller. We do have 1s. And we have 9s. The largest ever recorded instrumentally is a 9.6. There's a descriptor here, if they're moderate, great, etc. When it comes to the ground shaking, as you go up in magnitude from one to the next number, it increases tenfold. So what that means is, for example, a magnitude 5 creates 10 times more shaking than a magnitude 4. And as a result, the amplitude of that squiggle on a magnitude 5 would be 10 times higher than on magnitude 4. Energy released, however, is different and more. So the energy released increases for each magnitude number by 32 times. And so what that means is a magnitude 4 will release 32 times more energy than a magnitude 3. Another way to think about it is you would need 32 magnitude 3s to equal the energy released by one magnitude 4. And when you start going up higher in the magnitude scale, imagine 32 magnitude 7s equaling the energy of one magnitude 8. So it's very interesting how that scale increases. Another thing that's kind of interesting is that the 32-fold increase in energy released is multiplied as you go up the scales. So for example, a magnitude 4 releases 32 times more energy than a 3, and a 5 releases 32 times more energy than a 4. So a 5 would release about 1,000 times more energy than a magnitude 3, 32 times 32. Or you would need about 1,000 magnitude 3s to equal the energy released in a magnitude 5. On the right-hand side, we have the average number of events worldwide. And fortunately, you can see that these are inversely related. We have a large number of small earthquakes and a very small number of large earthquakes. Thank goodness, right? This is another way to look at the energy released. We have magnitude on the left scale and then equivalent kilograms of explosive on the right. Now notice that each of these numbers is lined up with each of these magnitudes, and it is 32 times greater each time you go up. A moderate lightning bolt is down here, the Oklahoma City bombing is here, the large lightning bolt is here, your average tornado releases this much energy, the Hiroshima atomic bomb is here, Mount St. Helens, world's largest nuclear test, and the Krakatoa eruption. So those are all listed for comparison. And then on the other side of the scale, we have earthquakes. Now, the Chile earthquake in 1960 was the largest one that we've ever recorded. It was a 9.6. The Alaskan earthquake in 1964 is the largest earthquake we've ever recorded in North America, and that was a 9.0. Then there are some other notable ones here. The Loma Prieta earthquake that I showed you photos from in the beginning is around here. That was a 6.9. So remember, this is a quantitative measure, not a qualitative measure like intensity. One last thing I just feel like I need to mention, we are not in this class going to have time to talk about the Earth's interior in terms of earthquake information, but I just think it's really cool to let you know that the only way we know how big the Earth's core is thanks to earthquake waves that pass through the Earth's interior, come out the other end, and are recorded by instruments, and they basically create some shadow zones when they hit the core mantle boundary because there's a big density change. I'm not going to go into it. But the point is, we really wouldn't know what was down there if it weren't for earthquake waves. We can't drill down there. The deepest we can drill is a couple miles into the crust. So that's just kind of a fun fact. All right, so in summary, there are two ways that we measure the size of an earthquake. The modified Mercalli scale is a qualitative scale, Roman numerals 1 to 10, and usually the greatest values are around the earthquake epicenter. But remember, there are some factors that it depends upon, such as the distance from the earthquake and the local geology. The moment magnitude scale, which is modeled after the Richter scale, is quantitative, 1 to 10, and the same value no matter where you measure it. So if there's an earthquake in California, let's say it's a magnitude 7, Japan would measure it on their instruments as a magnitude 7, and New York would measure it on their instruments as a magnitude 7. So the number would be the same everywhere. And remember that a magnitude 8 releases 32 times more energy than a magnitude 7, and 1,024 times more energy than a magnitude 6.